Hi, my name is Michael Marthaler, and I'm here to present my company HQS that I co-founded. And at HQS, we make simulation software with the goal that this software should run on quantum computers in the future. And the reason for this is that quantum computers offer really a lot of interesting opportunities. So if you would want to calculate the magnetization of a small metallic sphere, really small, just a few atoms. And I would give you the computational power of all existing computers combined to solve this problem. Then you would still need a few billion years to solve it. Now, with a quantum computer, you could solve the same problems within a few minutes or at most within a few hours. And so what this means is that a quantum computer can be more powerful than all existing computers combined for very specific problems. But there's a reason why we currently don't use quantum computers yet, and I want to explain this shortly. Now, the basic unit of the existing computers is the bit. The bit can have two states, 0 and 1. And you can imagine now this as an arrow, and if the bit is in the state 0, the arrow points down, and if it's the state 1, the arrow points up. The basic unit of the quantum computer is the quantum mechanical bit, the qubit. And you can imagine this again like an arrow, but now this arrow can point in any arbitrary direction. And this is the reason why the quantum computer can be very powerful for specific problems. But there's also a problem. Imagine again the bit, and you want to be in the state 1, so the arrow points up. And now some perturbation changes the direction of the arrow, but the arrow still roughly points up, and therefore you still know this is the state 1. For the qubit, this is different. Now you want to be able for this arrow to point in any arbitrary direction, so any perturbation creates a small arrow that accumulates during some calculation. And therefore, quantum computers can be very powerful, but they also are intrinsically sensitive to errors. And this is exactly the topic that me and my co-founders have worked on in academia since 2013. And we have worked on the exact origin of this error, so what kind of materials or other effects lead to these errors. We have worked on the mathematical description, and then we have used this knowledge to work on applications for quantum computers that work despite these errors. And the particular application is simulation, but simulation of molecules and materials. And the reason that this can work is because molecules couple basically to some type of environment which acts on the molecule. And this is kind of similar than the quantum mechanical bit that couples to environment. And this environment is the origin of these errors. And what you can do is you can map the quantum mechanical bits and their environment to the simulation of some type of molecule or some material and their environment. And so you can make algorithms that integrate to some extent a certain amount of errors into the algorithm and therefore become more resistant. Well, this is a way to describe it, at least, to this kind of errors. Now, the area where you would want to have this type of simulation technology is in material development. Material development has 3 stages: design, synthesis, and analysis. And so first, you would make a guess of what kind of chemical structure you would need to have for your specific properties that you want to have in your end product. Then you synthesize it, and then you analyze it. And synthesis and analysis, they are very expensive and time-consuming. So already in the design stage, you want to make a really good guess of what kind of material and what kind of chemical structure you want to use. And it is here where microscopic simulation of molecules and materials can be hugely valuable to speed up the overall development cycle and allow you to much faster arrive at your final product. Our company has been founded by our team, by me and my co-founders, and we have worked together since 2012. And Iris has worked on kind of the mathematical description on quantum computers with errors. And Rainer has worked on quantum algorithms, and Sebastian Zanker has worked in the past on amorphous materials, and Iris today is responsible for our business operations. Jan designs new algorithms, and Sebastian kind of outlines our software development and our general product development. And I lead the company in total, kind of have an overall view and keep the kind of overall technology roadmap aligned, and also combine this with doing a lot of business development. We have launched the company in 2017. We're located in Karlsruhe, and we are a spin-off of the Karlsruhe Institute of Technology. Currently, we have about 20 employees, all experts in quantum mechanics, quantum computing, or materials. We have already started or launched our first product, and it's called Quantum Assisted Design or Quantum Assisted Design Cloud. It's a cloud service where you can use quantum-based simulation methods that allow you to design new materials. And it's like a cloud-based simulation service. And what this allows you is to build this into your workflow. And currently it's still using conventional computers, but if you use this kind of cloud service, the transition to quantum computers will be extremely seamless, because only at the back end we change kind of which computer is called. Then it will be much more powerful, but basically for the end user there will be not much change. And as we look further into the future, there are many more opportunities for quantum computing. We start to get into the field with this very clear idea of doing simulation of materials or molecules. But then as we look further, there are really interesting algorithms that can be used for simulation of larger objects like cars or planes. And as we look even further and quantum computers develop ever further, there are also very interesting opportunities for quantum mechanically kind of enhanced artificial intelligence. And with this, I come to the end of my presentation, and thank you for listening.